Watching this video until the end means receiving ancient knowledge.
Imagine standing on a 1st century Welsh mountainside. At the moment Roman engineers pull the plug, millions of gallons of water, held in high-altitude tanks, are suddenly unleashed down a steep, rocky ravine. This was hushing, the weaponization of gravity and fluid pressure to physically rip the mountain apart. It was a calculated effort to strip away the topsoil and expose the gold-bearing quartz veins hidden inside. 2,000 years later, archaeologists and specialist recovery teams are still searching the valleys below, trying to map the exact locations where that ancient, auriferous runoff finally settled. Finding these sites by sight alone is nearly impossible. To an observer standing on the bank, a flowing river appears chaotic and unpredictable, hiding its deposits beneath layers of shifting gravel. But the water is actually a highly predictable, mathematically governed sorting machine. Every pebble and every grain of gold responds to the same set of rigid mechanical laws. To locate the lost hoards of the Roman Empire, we have to look past the surface and decode the unyielding laws of fluid dynamics. The process begins with the density disconnect. Common river quartz has a specific gravity of roughly 2.6. Native gold, however, sits at 19.3, making it more than 7 times heavier than the rocks surrounding it. Because of this weight, gold is incredibly stubborn. It can only be moved during high-velocity floods that generate enough shear stress to lift the heavy particles off the bottom and push them forward. But as a flood subsides, the gold reacts instantly. The moment the water's velocity drops below 2.5 feet per second, the kinetic energy is no longer enough to keep the metal in suspension. It plummets to the bedload, while the lighter gravel continues to wash downstream. This creates the first natural trap, bedrock crevices. At the very base of these cracks lies a laminar boundary layer, a microscopic zone where the water velocity is effectively zero. Once a gold flake slips into this zone, it is shielded from the current and remains locked in place for centuries. The second trap occurs at the inside point bars of river meanders. Centrifugal force sweeps the high-velocity, erosive water to the outside bend, while the inside curve slows down, causing heavy minerals to drop out of the flow at the upstream apex. Finally, there are boulder eddies. When fast-moving water hits a massive obstruction, it creates a low-pressure vortex on the downstream side. This sudden drop in pressure sucks heavy particles straight to the bottom, where they settle in the gravel pocket behind the rock. These 3 geomorphological features function as a permanent, natural sluice box that never stops catching heavy materials. Across the structural drainage networks of Roman Britain, these natural traps became the focus of the largest mining operations in the ancient world. Local Celtic tribes understood these traps on a basic level, using sheepskins and simple troughs to recover gold from shallow gravel benches, wealth that was often used to forge intricate jewelry like this torque. But the Roman invasion industrialized the process. Engineers constructed vast networks of aqueducts to channel water for the express purpose of large-scale hushing. When they unleashed these engineered floods, they didn't just move soil. They washed millions of tons of gold-bearing mountainside directly into the river systems below. This massive influx of material overloaded the natural bedrock cracks and inside bends, creating deep, highly concentrated deposits that followed the river's path. Roman engineering hijacked the river's natural depositional basins, turning them into high-concentration catchments that are still holding artifacts today. Modern historians and recovery specialists locate these undisturbed sites by applying a forensic routine called the 5-step stream scan. The first step is mapping the gold line. By drawing an imaginary vector connecting the inside apexes of the river's bends, we can trace the exact path the heaviest minerals traveled during the ancient floods. In these target zones, you must ignore the shifting surface sand. The goal is to reach the heavy cobble layer, a horizon of tightly packed, water-worn boulders resting directly on the bedrock or clay. This is where physics and archaeology collide. Because native gold and Roman industrial waste share nearly identical densities, they are governed by the exact same rules of motion. They plummet at the same velocity and wedge themselves into the same deep, rocky horizon. Locked within the slurry around these boulders, you will find a specific forensic signature, fragments of heavy, smelted Roman slag resting directly alongside raw native gold. Finding this specific matrix of natural metal and artificial slag maps the exact sediment plume of a 2,000-year-old industrial operation. By mastering the physics of the water, we can peel back the surface of a modern stream to read the permanent, ancient footprint of the Roman Empire. Once you identify the surface hydraulics of a river, you can pinpoint exactly where heavy minerals drop out of suspension. But reaching those minerals requires moving past the top layer of the riverbed. Gold does not sit loosely on the surface. Its extreme density causes it to migrate downward through shifting gravels until it hits an impenetrable barrier, either solid bedrock or a compacted false bottom known as the wet stratum. This geological layer formed during the Pleistocene epoch. Advancing ice sheets acted like industrial ore crushers, physically grinding down entire quartz veins across Scotland and northern England. These boulders are the remnants of that process. When the glaciers melted, they deposited billions of tons of mixed debris, or glacial till, creating terminal moraines across the lowlands. Modern rivers cut through these ancient moraines today. They wash away the light silt and concentrate the pre-ground gold into rich, localized pockets deep within the riverbed. These pockets are often buried under 1 to 3 feet of dense, magnetic black sands and packed ironstone cobbles. When an object like this Celtic gold torque settled into the river centuries ago, it became encased within this mineralized layer, which acts as a shield against standard detection. Standard very low-frequency detectors hit this black sand and are blinded by electromagnetic ground noise. They cannot distinguish the signal of the gold from the background interference of the iron. Successfully retrieving these objects requires a method to bypass both the physical depth of the glacial debris and the electromagnetic barrier of the black sands. Advanced pulse induction is the configuration required to penetrate this mineralized shield. This diagram represents how standard VLF machines fail. They emit a continuous sine wave that reacts with the magnetic ground, flooding the machine with noise. Pulse induction operates differently, firing brief, high-energy bursts of electromagnetic current straight into the soil. Because magnetic black sands are poor conductors, their induced magnetic fields decay almost instantly. On this timeline, the ground signal drops to 0 the moment the pulse shuts off. The machine utilizes a specific microsecond pause, the ground balance delay. It waits for the ground noise to die out completely before it starts listening. Only then does the sample window open. It catches the longer-lasting eddy currents bouncing off highly conductive targets, like native gold nuggets or ancient coin hoards hidden deep beneath the gravel. Pulse induction uses precise timing to isolate the signal of history from riverbed noise. Once a specific target is pinpointed beneath the surface, the operation's focus immediately shifts to the physical challenge of excavating in fast-moving water. To manage the current, you place a heavy boulder directly upstream. This splits the flow and creates a low-pressure eddy over the dig site, preventing the river from washing away your concentrates. You clear the top layer of river cobbles by hand to expose the bare bedrock surface. Using a shovel at this depth is counterproductive, as it can scatter fine gold directly into the current. Because coins and nuggets settle in the deepest vertical cracks, you use a specialized hand suction dredge tube. This pulls the dense slurry directly from the crevices and into a localized catch bucket. This manipulation of fluid dynamics is the only way to lift a target to the surface without the river current carrying it downstream. Successfully retrieving an artifact is the first step. The final challenge is navigating the ancient British property laws that govern these discoveries. The law treats natural alluvial gold flakes very differently from man-made historical artifacts. Under the doctrine of mines royal, all unextracted gold and silver in the UK belongs to the sovereign. While recreational panning is generally tolerated with landowner permission, the gold itself remains under the jurisdiction of the Crown Estate. If you uncover a man-made hoard, such as these Roman gold coins, the legal status is defined by the Treasure Act of 1996. Finders are legally obligated to report these discoveries to a local fines liaison officer within 14 days. Failure to report a hoard is a criminal offense. Once a find is processed through the Portable Antiquities Scheme, it is valued. If a museum acquires the find, a financial reward equal to the full market value is split between the finder and the landowner. Navigating the British riverbed is a technical discipline. It combines an understanding of Pleistocene ice sheets and pulse induction timing with a strict adherence to Crown law, ensuring that every discovery is both physically retrieved and legally preserved.